would show that one can indeed achieve this goal of 1% eventually on channels such as pi plus, pi minus, for instance. Now let's come to the second hadronic contribution, which is this hadronic light by light scattering. So this has a strong dependence, so the estimate, which I've shown you before, actually has a strong dependence on hadronic models which are being used. And in order to reduce this dependence on these models, one would like to use, of course, as much data as one can. And so this means one needs to measure quantities such as pion going into two photons, either one real, one virtual, in order to validate the models, which one then needs to calculate mu. And also one needs to measure this in the most relevant range of virtuality. So typically the low Q-squared range, so for instance, if a pion decays into two photons and one of these photons is time-like, it can go into a plus, a minus. It's the low Q-squared range which will contribute most to this anomalous magnetic moment. So yeah, as was pointed out, you need, it's a two-loop diagram. So just to remind you, it's so what is here is a two-loop diagram. So you need to integrate over two virtualities, basically. I will show you this in a little bit more detail later on. And so this means that in this integration range, so you will need data both where photons are time-like. So for instance here, this is so-called Dalitz decay of pseudoscalar mesons, or when photons are space-like. And space-like you obtain by also having E plus E minus scattering, but instead of annihilation, so where E plus E minus go into one photon, E plus E minus scatters by exchanging one photon, and E plus scatters by exchanging a second photon, and this is called photon-photon fusion. So you have a fusion of two photons into hadrons. And in a scattering process, the photon is always space-like, so its virtuality is negative. So this is a pure space-like process. Here you have time-like process. So you can basically combine measurements from different facilities. So if you have facilities where you can look at the decay of these states into E plus E minus final states, or if you do fusion processes, so this part is done also at BESS, and this part is done at facilities such as Maui, for instance. Let me give you an idea, what is the status here, and also which kind of physics one is accessing. So basically, the simplest process of a fusion of two photons, how to understand it in QCD, is through a so-called handbag diagram. So it's basically a quark. So two photons, they give rise to a quark-anti-quark, to such a diagram. And this is the wave function of a meson, for instance a pi 0, in a quark-anti-quark. So it's basically the leading so-called Fock component, quark-anti-quark component of a pion. And technically people call this a meson distribution amplitude. So it tells you what is the probability amplitude to find, for instance, a pion in a state of UU bar or DV bar. So this is a paradigm for a whole program of hard processes which are planned at different facilities, so at Jefferson Lab and Compass, and also at colliders which are being discussed, the next generation of colliders. And it's also from the point of view of perturbative QCD, most probably one of the simplest processes where one can study the transition regime to perturbative QCD, which still remains to be understood. And actually, to give you an idea of the status of the data, so this process has been measured up to about 35 GeV squared. So when one photon is real and one is virtual, so one plots the virtuality here of this photon, and one can describe this then process here by a form factor, and you can easily work out, so this is a perturbative diagram, you get here one propagator, so this height scale which flow in here, and this will tell you that this form factor has to scale as 1 over q squared. So if you multiply this form factor with q squared, you should find a constant. And actually, in the leading perturbative QCD description, if you take a so-called democratic sharing, one calls it maybe, between the quark and the anti-quark, which means that the probability to find that this quark has a certain momentum fraction and the anti-quark has then 1 minus this momentum fraction, so they're basically moving collinear. So is the same. So one has equal. So when it's 1/2, then you have a maximum. So this is so-called asymptotic distribution amplitude. Then you can predict this constant, and this constant actually turns out to be 2 times the pi on decay constant. So and this gives rise to a line. People calculated, of course, this process already corrections. So when you have next to leading order corrections, you would have gluons here, and people did it even up to 2 loop level, so next to leading order. And typically, what this calculation shows is that this leading order prediction will slightly go down. Typically, it goes down like by 10% here, and then at low Q-squared, of course, there will be a bend. Now the data, so situation is not completely clear. There are two. So at low virtualities, there were older data, basically by Clio. So the more recent ones, they show indication towards this line, but most recent measurements by Babar and by Bell are not in agreement, although the error bars here are large, but even in the intermediate range, there is a clear discrepancy. Now, this is still, of course, an ongoing debate, so but what it does show is that these quantities here are in the range of this constant line, although the normalization is not exactly given at this scale. So it shows even the simplest process here in terms of perturbative QCD is not understood at the level, typically not understood at the level better than 10%, let's say. So now you can ask, so what is the impact for this anomalous magnetic moment of the muon? So the impact on the anomalous magnetic moment of the muon, so this is the same plot, but now the low Q-squared range. And what is shown here in red are not data, so they are hopefully data. So this is simulation. So for data which will be obtained in 1 year of running at best 3. Now, I have to say, I cannot show them, but we have experimental colleagues in Mainz working at best. Actually, they do have data already now, and the data do show the same precision as these red points. So basically, such data already exists, but they're still working on the normalization. So it's basically the region here up to about 3 GeV squared is the dominant region for this light by light contribution, and in this regime there are very few data, so most of the data are at larger Q squared, but very few at low Q squared, so best 3 will nicely fill in this gap. So, okay, let me, by giving you this general introduction here to this field, so this is about half of my time, I see. Is that correct? Yeah. So I will, of course, not be able to give you all the technical details of the theories which are being taken or which are ongoing, but I would like to give you some flavor at least, so how to address this problem. And so the first is, how do we understand the scattering of 2 photons into hadrons? So, and a very strong theoretical tool, model independent tool, are sun rules, so they can tell you a lot. And so I would like to give you some ideas on some recent developments on these sun rules for 2 photon fusion processes. And so let me just start by the simplest of this process, namely the scattering of 2 photons, here with momentum Q1 and Q2, velocities lambda 1 and lambda 2, into 2 other photons, but with the same momentum. So this is so-called forward scattering. So no momentum transfer, so this momentum is the same, and this momentum is the same, but the helicity can be different. Now, so what is the helicity of a photon? So what can be the helicities of the photon? Which values does it take? 2, if you have real photons, and if you allow, we have seen we like to have virtual photons, like E plus E minus going to photon, or so then you have 3, so which means 0, 1, plus 1, and minus 1. So you have 3 possibilities for each of these helicities. So we would like to characterize the number of amplitudes which describe such a process. Now, kinematically, you can describe this in the usual way. You introduce the invariance, which is the center of mass energy squared, the sum of the two, and then you have a crossing variable u, which is then the difference of the two squared, and you can define then the energy, which is the crossing variable, as minus u. This will be the energy variable I'm using, and then you have the two virtualities. So each photon can be virtual, and we define its virtuality as minus the 4 momentum squared of this one, and minus the 4 momentum transfer of this one. So you have basically 3 independent kinematical variables, the 2 virtualities, and the crossing symmetrical energy variable. So yeah, we can describe this by helicity amplitudes. So we have 4 helicity states, and they are functions of these 3 variables, and each of these helicities can take 3 values. So last time we went through this derivation in the case of elastic electron-proton scattering. So what are the number of invariant amplitudes? So we have seen that using parity and time reversal, one arrives at 6. In the case of spin 1/2 on spin 1/2, so here we have basically spin 1 on spin 1. So if you have 3 helicity states, I can ask you the same question as last time. So how many amplitudes do you have in total? There will be many more in this case. So without applying any symmetry, if you just count, how many amplitudes would you count, just based on the helicities? 81 indeed. Mm-hmm. And now you have to do some work. So you have to apply if you assume, of course, parity invariance and time reversal invariance. So we have seen with parity you are changing helicity to minus helicity. If you say the amplitude should be the same or up to the phase the same. And time reversal means if you exchange the helicity of initial and final state, they should be the same. You will get a lot of constraints. And I will leave it as a homework for you to figure that out, but it can be done along the same lines as we have done before. You come down to 8, so there's quite some restriction here. So from 81 to 8. Yeah. And you can characterize these 8s in 2 groups. There are 3 amplitudes which involve, so what I'm going to indicate as plus and minus means plus and minus 1. And the 2 right indices are the initial state helicities, and the 2 left indices are the final state helicities. So for instance here, this means you have positive helicity for all the photons. So when the photons in the center of mass frame are coming in, the spins point in the same direction, and they stay positive from initial to final state. And here you have 1 positive and 1 negative helicity. And here you have 2 negative helicities, which are going into 2 positive helicities. So it's a double helicity flip amplitude. So they involve only plus or minus, which means transverse photons. And then you have 5 amplitudes which involve zeros, and 0 means you have a longitudinal photon. So if you go to the limit when the virtuality is 0, then only 3 amplitudes survive, which are these transverse photon amplitudes. Now you can relate this process then, or these amplitudes, helicity amplitudes, the imaginary parts, you can relate them by the scattering of 2 of these virtual photons into hadronic final states. So through the optical theorem or unitarity, and this gives you rise to cross-sections. So this imaginary part, the optical theorem, allows you to write it as a phase space integral. So this is the usual phase space integral of a square of 2 of these amplitudes. So this can be expressed in terms of gamma star to x cross-sections, which can be measured. So in the end, we would like to connect this to experiment in order to have as model independent constraint as possible when we use it in this G-2. And I will not go through all the details here, but just to give you some flavor, these are the 8 cross-sections which basically enter. Let's just look here at a few of them. The top line, if you take these helicity amplitudes where the 2 photons are either both positive or both, or one positive, one negative. So this is the same as the so-called unpolarized cross-section. So when you average them, and then you get, so this is usually called sigma TT, so both are transverse photon, this is the unpolarized cross-section. Now you can take the difference between the two, so this is the difference when you have one photon which has positive helicity, the other positive minus negative. So this is a helicity difference, so on a spin 1/2 target, this will be the unpolarized structure function, this is the longitudinal polarized structure function. So this gives you a second quantity. And then there's a third quantity, which I would also like to point out, when the 2 helicities go from negative to 2 helicities positive. So a double helicity flip amplitude, which is here. And then you have a number of cross-sections which involve longitudinal photons. Now, how can you measure them? So I was saying that these things can be accessed in the scattering of electrons and positrons, where you detect the scattered electron and the scattered positron. So you have typically these barrel detectors, so you tag them, and due to this tagging, so detecting them, you can measure the virtuality of either of these 2 photons, and then you will measure here the final state. So this, again, the details are not of relevance. The only thing I would like to show, this is all related to experiment. So the cross-section here is basically a phase space over the first measured electron, the second measured electron, positron in this case. Everything in black are just kinematical factors, so they are well known. And then you see, depending on these 8 cross-sections, they enter in this cross-section. And some of them, they have, very similar to the case for spin 1/2 target, they have angular dependencies in them, like the cosine phi or cosine 2 phi, or here another cosine phi. And this phi is the angle between the 2 lepton planes. So if you define, for instance, this to be in one plane, this positron can scatter out of the plane. So there's one relative angle there, which is coming in. So by doing these measurements, tagging at different angles, you can in principle access these different functions. Now 2 of them involve here helicities of the lepton beams. So these have never been measured up to now at the E plus E minus colliders. So polarized colliders don't exist yet. So but to access these 2, you would need polarized electron and positron beams. Okay, so let me show you, let's assume we have enough of these measurements of these cross-sections. So how can we reconstruct the real part of the amplitudes? So typically you do this by causality, and you write down dispersion relations. So we have amplitudes which have a definite behavior under photon crossing, so which are either even or odd under this when you change the energy variable. And then you can write down, depending on which case you are, you can write dispersion relation, as you know from quantum mechanics, so you relate the imaginary part of even or odd amplitude to its real part as an energy interval. So the only difference between this even and odd is that the powers here will be different. So here you will have a high energy behavior like 1 over nu prime, and here you will have 1 over nu prime squared. So this will be faster convergent, for instance, than this one if they have the same high energy behavior. So yeah, one needs, of course, to look how is this high energy behavior. So if it's not fast enough, one needs to do a subtraction and fix this subtraction constant. Also similar, we have seen one such example in the first lecture. And then let's assume we have reconstructed these real parts. In order to calculate them now at low energy, because we will need this for the anomalous moment of the muon, we want to reconstruct them at 0 energy, let's say, or at very low energy. So we are doing a low energy expansion for these amplitudes around energy 0. And this low energy expansion actually was, the leading term was written down quite some time ago by Euler and Heisenberg in 1936. So if you just, people ask you, you have a theory, effective field theory, where you integrate out all the degrees of freedom except photons. So how do photons interact with themselves? So there is no point coupling, evidently. But if you integrate out the degrees of freedom, two photons can go to a box diagram, lepton box diagram, into two photons. And if you go to very low energies, which are typically much lower than the mass of the electron, you can basically shrink this box to a point, and then you have an effective coupling in that way between two photon fields to photon fields. So we know we need to write down a Lagrangian which is scalar, which is gauge invariant, Lorentz invariant. So gauge invariance means if you have only photon fields, it should only be composed of field tensor or dual field tensor. And so because it has to be scalar, so basically, so you need to take here the product of two of them, and because you have 4 photon fields, you need to have 4 of these, so the square of that would be the one term. And then you can take the product of a field tensor which is dual field tensor. So this is like, in electric and magnetic field, this is like a scalar product of E dot B. So this is pseudoscalar, and we know the Lagrangian should be a scalar, so if you square that, you will get another scalar. And at leading order, so this is, if you do an expansion in energy, this will come at energy to the 4th power. This will be the leading term. It's characterized by 2 so-called low energy constants, and they describe the low energy light by light scattering. Now you can, so I will come back and I will quantify these constants. So if you have hadronic intermediate states and so on, they will just, all this information is composed in these numbers here. Now if you go to the next order, order energy to the 6th, you will get actually 6 new energy constants. So we quantified this some years ago, and then you can you can write down the different terms to the next order. They involve derivatives then of photon fields and so on. And so if you know these different low energy constants, you can basically then describe it to somewhat higher energy, this process. Okay, just if you apply now these dispersion relations, it turns out that you can find 3 so-called sum rules or superconvergence relations. So a superconvergence relation is a difference between 2 sum rules where one of the sides drops out, so you have a 0, and then on the right side you have an energy integral over some imaginary part, and I wrote it here in terms of cross-sections, and sigma 0 and sigma 2 are cross-sections where the 0 and 2 indicate the total helicity of the 2 photons. So if the helicities are pointing like this, the total helicity is 0. If they are pointing like this, it's 2. So this is the equivalent of the longitudinal spin structure function. So it's the difference between one helicity combination and the other helicity combination. When one of the photons is real, so let's say Q2 squared, the virtuality is 0, and the other is virtual. So you have here this factor comes from the denominator in this dispersion interval. So at Q squared 0, this corresponds actually for spin 1/2 target to the Gerasimov-Traverse sum rule. So this is the generalization for photons. And so we found that you can write down 2 more of these sum rules, which involve longitudinal photons. So I will not go into details, but these other, so there were 8 cross-sections, as I've shown you. They involve here transverse and longitudinal photon cross-sections, and here also combinations also involving longitudinal photons. So in total, you can find 3 of these superconvergence relations. And then if you go one order further, you basically fix these low energy constants. You find sum rules which can determine either the sum or the difference of these 2. So this is shown here for the leading low energy constants which are entering this order Heisenberg-Lagrangian. You get the sum of them by, so sigma parallel and sigma perp actually refer to the fact if you do experiments with linearly polarized photons, so the 2 photon polarizations can be parallel or they can be perpendicular, so when they're moving like this. So, and if you do the average, it's again the unpolarized cross-section, so the sum of them corresponds to unpolarized cross-section, and the difference between these 2 configurations, they allow you to disentangle these 2 low energy constants. And again, if you go to the next order, you can write down some rules also for the next low energy constants, which correspond to the next order term. So, okay, I will show you one example here. So how can you verify these sum rules? First of all, in perturbative quantum field theory. So if you have this is a general relation, so it should come out of any quantum field theory, and before we apply it to data. So the simplest one is really just scalar QED. I'll just show you this one example here. So if you calculate scalar QED at 3 level, it's the simplest calculation here you can do. So imagine these are spin 0 particles. So you know 2 photons coupled to this by 3 diagrams, and this is a charged particle. So basically the direct, the cross diagram, and then for gauge invariance you have a contact diagram. And you can calculate then these cross-sections. Actually, this difference of cross-sections has a nice simple analytic formula here involving the log and the square roots. And if you plot the integrand here as function of the energy, so this is shown here, this should integrate to 0. So what you see basically is that, so this is here as function of the virtuality of one of the photons. So one of the photons is real, so Q2 squared was 0, and the other is virtual, and then you look at different virtualities. So this is when both photons are real. So you see at lower energies, so this is as function of the energy, so it's negative, which means that the photons have preferential orientation, so anti-parallel, so the total helicity is 0. If you go to high energy, they tend to prefer parallel orientation, so the cross-section sigma 2 is dominating. And if you integrate this area exactly compensates this area, and this is also valid, of course, when you go then to virtual photons, these red lines, so the cross-section just becomes smaller and become shifted, but it will always integrate to 0. You can do this also, of course, with QED. I will not go to that. You can do it at one loop level, 5 to the 4 theory. So we have done a whole range of checks also in theories like where you can resum some diagrams, and basically we have done a resummation to all orders within 5 to the 4 theory, so these sum rules are just exactly verified. So let's now use them as a practical tool to see if you produce hadrons. So what can we learn from those sum rules? So if we produce hadrons, so mesons typically, so these two photons give rise to a meson, and this meson has quantum numbers, total angular momentum, parity, and charge parity. So what's the C parity, charge parity of a photon? C quantum number. So it's a vector. So it's minus. It will be minus. So you will have, and you have two of them. So you can produce in such a process mesons which are eigenstates of charge parity charge conjugation operator with a quantum number +1. So for instance, a pi 0 has positive charge parity, but states which have negative charge parity, vector mesons, for instance, you cannot produce. So you cannot produce all mesons here. So you basically only need to consider states which have positive charge parity. Now, if you have, instead of virtual photons, if these photons are real, you have an additional symmetry or constraint. Namely, if you have two real photons, you cannot produce states which have angular momentum 1. So this is a little bit more difficult to explain you, at least intuitively. So it's so-called Landau-Yang theorem. It's related to the fact that you have a Bose symmetry in addition. So two real photons are indistinguishable state. And you can see that if you do the coupling of two of these states to a spin 1, there will be a Clebsch-Gordan coefficient which basically will give you 0. So in the end, so if you have real photons, there is no angular momentum 1, so only angular momentum 0, J, and positive C parity, or angular momentum